Hello students, in today's video we're going to work on modeling and optimization. So let's go ahead and get started. Now when we do optimization, we want to basically maximize or minimize some aspect of it. So some of these examples might include maximizing profit, maximizing area, maximizing volume, minimizing costs, or minimizing material used to produce a good. So here are 5 quick and easy steps to help you when approaching these types of problems. They don't give you a lot of equations, so you kind of have to follow these as a guide. So write an equation of a single variable that represents the quantity you are trying to optimize, graph the function and determine the domain, find the critical points and endpoints, solve the mathematical model, and then interpret the solutions in terms of the original problem. So go ahead and write these down and we'll try this problem together. Now it says an open top box is to be made by cutting congruent squares from each corner of a 30-inch by 40-inch sheet of a tin and bending up the sides. How large should the squares be to make the box hold as much as possible? What is that resulting volume? So there's a lot of things in there, but essentially we want to maximize the volume of a box from a 30-inch by 40-inch sheet. So first thing we want to look at is having a diagram to kind of help us out. We know that this thing is 30 by 40 inches. And then what we're going to end up doing is cutting squares off of the side. So what's happening is we are cutting pieces off like so. And obviously they're going to be equal length, even if I'm not necessarily drawing them perfectly. Okay, and each length is going to be x. Now, what we're trying to do is maximize volume. So remember, volume is equal to area of the base times the height, or in this particular case, it's length times width times height. So for this volume, we know it's going to, the length is supposed to be 40 inches, but keep in mind that we're subtracting a small piece from each side. So it's going to be 40 minus 2x. Our width is going to be 30 minus 2x, and our height is just going to be x. So just a reminder, this whole side from here to here is 40, but we're cutting off this side right here, which is x, and this side right here, which is x. And so that's how we get our volume. Now, what we're going to do now is we're going to take that value and we're going to multiply that out, or FOIL that out. What happens is we get volume is equal to 4x cubed minus 140x squared plus 1200x. Now, the next thing we're going to do is we're going to find the derivative of it. So we find the derivative, and we're left with 12x squared minus 280x plus 1200. And then from there, we're going to go ahead and factor this out. So when we do that, or use quadratic equation, we're going to get x equals 5.6. Now, I didn't give you the other value because it turns out to be negative. So you can use quadratic formula for this, or you can graph this on Desmos or your graphing calculator, but your positive answer is going to be 5.66. Because again, if we had a negative x, that means we are cutting the box a negative length, which is impossible. So the maximum height of the box, or length of the box, that we can cut is 5.66 inches. And then that max volume is equal to 3032. So when we look at the graph now, you'll see here that at 5.66, that's the highest value that we're going to have for this box. And that's 3032, which is that max volume. I know this graph continues to go on forever, but after that we're getting values that are irrelevant or they don't help us. because they're not within the constraints of our box. So, moving forward, let's look at another problem. So when we want to maximize profit, if it exists, now that occurs, maximizing profit occurs at a production level at which the marginal revenue equals the marginal cost. So the marginal revenue has to be equal to the marginal cost. Now, looking at example 4, it says suppose R of x represents a revenue and C of x represents the cost to produce x thousands of units. Is there a production level that maximizes profit? And if so, what is it? So, a couple things to keep in mind. Marginal revenue that's spelled wrong. Revenue is equal to R prime of x, and marginal cost is equal to C prime of x. So keep in mind, when we're trying to maximize or minimize things, we're always finding the first derivative, because that's, if you think about our graphs, that's our maximum or minimum. So, for example 4, if we are trying to maximize profit, we're going to have to set R of x, or R prime of x, equal to C prime of x. So when we graph that, or sorry, not when we graph that, when we set those two things equal to one another, we are going to get R prime of x is equal to 2x divided by x squared plus 1 quantity squared, and C prime of x is equal to x minus 1 quantity squared. And keep in mind, all we did here is we took the first derivative of R of x and C of x. And now, because we're trying to find the maximum profit, remember, max profit is when R prime of x is equal to C prime of x. So all we're doing is we're setting those two things equal to one another. So we have the following. Now, what's going to happen is we're going to need to solve this, or attempt to solve it. We're going to get something to the effect of 2x equals x squared plus 2. Well, basically, this. What we did here is we multiplied x squared plus 1 quantity squared to both sides, and that's why it's on the right side now. And what we're going to end up with is something that's not solvable. So let's take a look really quickly at that graph. Notice here at this graph, it doesn't really happen unless we produce 0. Okay, so we're looking at the graph in orange. And what happens is, if you notice how I graphed it, I set y equal to and I subtracted the two things. So what you'll find here is I don't really have a max or a min. And if we look back at our equation that we have, we can't exactly solve this for x because we're going to end up with a lot of mess. So if we try to simplify this even further, we get 2x equals x to the 4th plus 2x squared plus x times x minus 1 quantity squared. And so that's obviously, it's not going to work out for us. And as you can see on the graph, it didn't. So let's try another problem. Farmer John wants to build a rectangular pig pen on the side of his barn. He has 30 meters of fence. If he used the side of the barn as one side of the pig pen, how should he build the pig pen in order to maximize the area? So when we look at this problem, we're going to consider what we have. So first thing they mention is he has 30 meters of fence. That means the perimeter equals 30 meters. Then it says if he used the barn as the side of the pig pen, how should he build the pig pen in order to maximize area? So we're looking at a maximization of area. So area of a rectangular pig pen is length times width. So keep this in mind. If we say have a barn, here's our barn, and we're trying to create a pig pen, well, here is the pig pen in dashed. Notice I didn't use it here because we're using that side of the barn as our fourth side of that wall or fourth side of that pig pen. So now we have to look a little bit further into how we use that perimeter. We know that perimeter is typically 2L, 2 times the length, plus 2 times the width equals 30. However, because we're using one side of the barn, we don't actually need this extra W or extra L depending on what you want to use. And so what we're going to have here is we're going to know that the width is equal to 30 minus 2L. That's going to be really important because when we start looking at this area optimization, we can't have two different variables. So what ends up happening is we have L times W, and W is equal to 30 minus 2L. So the area is equal to 30L minus 2L squared. And that's the area for the pig pen given 30. Now what we need to do, if we're trying to maximize, is we take the derivative. So this becomes 30 minus 4L. That's going to be the first derivative for our area. Now what we want to do is take our 30 minus 4L and set that equal to 0, because we're trying to maximize. We find out that L is equal to 30 fourths, and that 30 fourths is equal to 7.5 meters. So the length has to be 7.5 meters if we're trying to maximize that area. Now we need to find that width. So remember, width is equal to 30 minus 2L, which means 30 minus 2 times 7.5. We find out that that width is equal to 15 meters. So if Farmer John is trying to maximize his pig pen, the width needs to be 15 and the length needs to be 7.5 meters if we're using one side as the wall. So let's look at a minimizing average cost now. So if we're trying to minimize average cost, we know that the production level at which average cost is smallest, if it exists, is a level at which the average cost equals the marginal cost. So average cost must equal marginal cost. Huge deal. So average cost equals marginal cost. Remember, marginal means we're taking the first derivative of the cost formula. So matching that up with our equation below, I'm going to rewrite it just so it matches the equation. So marginal cost equals average cost. So let's use this formula that we have here and work on the next problem. So suppose C of x represents cost to produce x thousands of units. Is there a production level that minimizes average cost? If so, what is that production level? So remember, we're doing marginal cost equal to average cost. So marginal cost equals average cost. Like so. So this is the formula we're going to be working with. Now, the average cost, or the marginal cost here, is the derivative of x e to the x minus 2x squared. So that's going to give us e to the x times 1 plus x minus 4x. That's going to be our marginal cost. Our c to the x, we already were given. It was x e to the x minus 2x squared, all divided by x. So we're just using that formula of marginal cost equal to average cost. We're going to simplify this a little bit more. And what's going to happen is we now have e to the x times 1 plus x minus 4x equal to e to the x minus 2x. And what you may have noticed here is I dropped the x's and we got rid of the denominator. What ended up happening is we have this x down here. And what happens is because we have it here and here, we can factor out one of those x's and cancel them out. And we're left with what you see here. So now that that's done, you are going to want to bring the e to the x over. So we have e to the x times 1 plus x. That minus 4x you see here, I'm going to add 4x to both sides. So 4x minus 2x. And this e to the x here, I'm going to subtract to both sides. I'm going to put that on our left side now, like so. Now that we have that, if you notice on your left side, we have e to the x in both terms. So I'm going to go ahead and factor that out, and you're left with 1 plus x minus 1 equals 2x. Simplifying, we have e to the x times x equals 2x. Because the 1 minus 1 goes away. I'm going to divide x to both sides. We're left with e to the x equals 2. And we have to keep in mind what these opposites are. So I'm going to do some work on the left side just to make this easier. So we have e to the x equals 2. If you remember, the opposite of e to the x is ln. So we have ln e to the x. But we have to do ln to both sides. So we have ln 2. And therefore we're left with x equals ln 2, which is approximately 0.69, which is 0.69 thousandths of 1,000 units. Now we can go further and put this into a much cleaner and better looking number, but we don't need that. So we're going to stop there. So we're going to try and minimize cost now. Actually, sorry, we just did that. So that's how we do that. I know you may have some problems, but we're going to work on this in class together. That's all for now. I'll see you guys next time.